We're going to begin with the motions of Earth by looking at rotation and revolution. Don't get those two confused. Rotation is the spinning of the Earth upon its axis, as it takes about 24 hours to rotate one time around, and that's what gives us our day and night cycles. Here's the axis right here. The axis is not straight up and down. It's actually tilted over to the side at about 23.5 degrees. That's why when you look at globes, they're always kind of tilted to the side as well. So it rotates one time on its axis once every 24 hours. And it gives us some apparent motion as well. When we look up to the stars at nighttime, this is a time-lapse photo down here. We can see it appears that the stars look like they rise in the east and then they would set in the west. And this is an apparent motion. It's us sitting underneath of it's like if you're on a merry-go-round at the playground and they're spinning really fast. It looks like the world is spinning around you, but it's actually you who is spinning. So the same effect takes place here. This is a time-lapse photo showing the trace of the stars rising in the east and setting in the west because we rotate underneath of them. We're going counterclockwise. So rotation takes about every 24 hours. Revolution takes 365.25 days. That 365 days is a year, but it's actually about 0.25 longer than that. And so that's why every 4 years we have to add a leap year, one extra day we add in to make up for that 0.25. As it revolves around the sun, it goes counterclockwise around the sun. We see the arrows right here. And because of the tilt in this revolution, we have seasons where it depends on the tilt in that hemisphere. We have the northern and southern hemispheres. So let me just draw those here. Let's deal primarily with the northern hemisphere since that's where we live in. Here's my equator here, and it's also tilted down a little bit because here's my axis right here. Here's my equator tilted downward a little bit. And then here's my equator. So we're showing the Earth at 4 positions during the year, during summer, winter, spring, and fall. And what gives it that, it has to do not with the distance from the Earth to the sun, not that the sun's putting out more energy. It has to do with the tilt and the revolution. Whenever the Earth is tilted away from the sun, you have cooler temperatures in that hemisphere. For instance, right here, we look at our northern hemisphere. We're tilted away from the sun here. We're leaning backwards and away from the sun. That would be winter time in that hemisphere. Over here on the opposite side, we're tilted towards the sun. So there's my tilt. It's leaning towards the sun. That would be summertime. It's like if you had a campfire. If you leaned away from the campfire, you'd be a little bit cooler. If you lean towards the campfire, you'd be a little bit warmer. So there's summer and winter. Now, spring and fall, it's kind of tilted off to the side here. You have to imagine this in 3 dimensions. It's not tilted towards the sun or away from the sun. And so these give you more moderate temperatures of the spring and fall, or the spring and autumn as they have it listed up here. And the way to determine that is you just have to remember counterclockwise. If you know where winter and summer is by whether it leans towards the sun or away from the sun, you just go counterclockwise. If this is winter right here, if we go counterclockwise, well, you just think, well, what comes after winter and before summer? Well, that would be spring. And then same thing over here. If we know this is summer as we go around, well, what comes after summer and before winter on our way to winter? Well, that would be autumn or fall. So that's how you determine the seasons. The other things I've seen that have popped up on SOLs and on tests are things like this in the top right-hand corner where it asks you a question like, which one of these letters would have the most hours of daylight? And what you got to remember is this. The hemispheres are opposite. Whenever I had the winter time up here, let me give it like a green color. Whenever I had winter time up here, the southern hemisphere, look down here where I'm drawn, is kicked towards the sun. It's always the opposite. And so down here in the southern hemisphere, it's summertime. And then down here in this hemisphere, where it's summer in the northern hemisphere, down south it's kicked away from the sun. So that's going to be winter time in the southern hemisphere. The southern hemisphere is always the complete opposite. They have opposite seasons. When it's summertime here in North America, it's winter time there in Australia. When it's Christmas time or winter time here in North America, it's beach weather. It's summertime down in Australia. So that's how you remember it. The daylight hours are longer in the summer, and the daylight hours are shorter in the wintertime. So when we look at this picture up here, we have, well, here's our sun off to the right hand side, and we see the northern hemisphere is tilted towards the sun, and the southern hemisphere is tilted away. And we can see that letter A up there as it goes around the earth. You see, this is all daylight hour on this side over here, and it's just a little slither of darkness over here on the left hand side. As it rotates around, and then as it goes to the back side, it's still daylight, 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 and then it hits this little slither of nighttime and comes back around. So it's mostly daylight hours here at A. If we're down here just below D, well, it's mostly nighttime as it goes around and it rotates, and then hits this little slither of daylight, and then goes back around and hits nighttime again. That's why during the wintertime it gets dark so fast. Sometimes it'll get dark like 5 o'clock in the afternoon, but in the summertime you can go till 8, maybe 8:30, 9 o'clock at night before it starts to get dark. Because summertime hours, the daylight hours are just much longer. The last thing is looking at these letters. We can see if this Earth is going counterclockwise, if it's going this way around, kind of orbiting around like this, we can see that A is in daytime. It had just passed through this transition. This line right here would be sunrise, because if the Earth is going around this way, whenever we're moving from darkness into daylight, this would be where sunrise is at. So C has just experienced sunrise, and D would be the next letter that comes up here and hits that. They call it the terminator line. It's where the boundary between daylight and nighttime on any celestial body occurs at.